Hello everyone, I'm Ishtiak. I'm currently pursuing a BSc in physics at Nanyang Technological University. And today we will be discussing Newtonian mechanics. Uh, to tell more about myself, like Olympiad recognition এর দিক থেকে আমি কয়েকবার physics Olympiad participate করছি, mainly physics Olympiad participate করতাম. Other than that, junior science Olympiad ছোটবেলায় actually participate করছি but didn't continue later. Um, Olympiad achievemenটের মধ্যে I have a bronze medal in not one actually. I have two bronze medal in International Physics Olympiad, and then I also have worked as mentor for both Bangladesh Physics Olympiad and Junior Science Olympiad before. All right, so let's jump into the topics. আজকের টপিক বেসিক্যালি আমি চারটা ক্যাটাগরিতে ভাগ করছি জেনারেলাইজড টপিকে. Those are Newton's laws. It's Okay, so topic গুলাকে চারটা generalized সেকশনে ভাগ করছি. First will be Newton's laws, then we'll discuss about different forces. অনেক টাইপের forces, but we will mostly constrict ourselves to the forces we generally see in mechanics problems. Then we will also discuss about force diagrams, and finally we will deal with how to apply Newton's laws to mechanics problems. Okay, now the topics seem very simple. So we start with Newton's laws. So more specifically, Newton's laws of motion. There are three laws. All of you should already know the three laws. এগুলো আমরা ছোটবেলা থেকে মোটামুটি পড়ে আসি। আমি যদি একটু simply বলি, the first law tells you that an object that is moving at a constant velocity keeps moving at the constant velocity. So it basically tells you, so first law, এটাকে যদি আমি একটা summarized form দেখি, I can write it as if A is 0, remember A is acceleration. This implies V is constant. Now, this is not exactly right, but then most people actually understand this by Newton's first law. We will discuss this in more detail, but then first হচ্ছে দেখে নি যে আমরা খুব short form এ নিউটনের তিনটা law বলতে কি বুঝি. So that is the first law, that if a body has zero force, actually not acceleration, it doesn't talk about acceleration here. It tells you that if the force is zero, that implies velocity is constant. So this is the first law, that if the net force is zero on an object, that implies it's moving at a constant velocity. Now, it might be a bit different from what you have heard, because the more general statement, like sometimes what you see in books, is a body that is stationary stays stationary, and something that is moving at a constant velocity keeps doing so. Basically, like if a body is moving like this, it keeps moving on this straight line indefinitely at constant velocity. Now, being in a zero velocity is also a constant velocity. So you can just summarize that as as it moves at a constant velocity. If it was zero, it stays zero. If it was some other value, it stays that value. Okay, so that is Newton's first law. What about second law? Second law এর form হইতে পারে sum of f is m times a, or if you don't like it, a more general version is that sum of f, these are vector sum, actually should put vector on all of these. So sum of all the forces, vector sum of all the forces, is actually derivative of momentum. But what is derivative? You're not required to know what a derivative is. You can just treat it as a change. So it's momentum's change with respect to time. So opore you have a fraction, opore আছে হচ্ছে change in momentum, and in the denominator you have the change in time. Remember, P is mv. This is mass, this is velocity, and then delta in general refers to the change. So delta P would just be, the whole thing would just be final momentum minus initial momentum. All right, and then for the third law statement, we basically talk about it as every action has an equal and opposite reaction. So every action has equal and opposite reaction. Now, these are the three laws. You should probably have heard of them before, but then আমি কেন হচ্ছে এগুলো নিয়ে আরো ডিটেল আলোচনা করব, because I'm not saying these are wrong, but these don't cover the whole picture basically. So for starters, what's wrong with this? For starters, if we take this to be the second law, F is equal to ma, then if your net force is 0, so let's take the second law. This is sum of F is equal to m times a. And then if the sum of all the forces is 0, that tells me ma is 0. That implies a is 0 because mass is not 0 for any classical objects. Any classical objects that exist, they have a non-zero mass. All right, so acceleration is 0, but then acceleration 0 implies velocity is constant. Now, what have we done here? What we have done is we have proved Newton's first law from second law. But then can we do that? We shouldn't be able to do that because a law means something that you cannot prove. It comes from some fundamental assumptions. If you can prove one from another, then this shouldn't be called the first law. এটা হওয়া উচিত বাংলায় বললে অনুসিদ্ধান্ত, something that you derive from the second law. Then why do people call it the first law? Because it actually tells you more than this. So let's go into actual first law. Actual first law, how you should think about it. So it tells you that there exists a reference frame where if sum of all force is 0, then A is equal to 0, or equivalently, V is equal to constant. So it doesn't say that if net force is 0, velocity is always constant. It says there is a specific reference frame. There's a specific reference frame where if the net force is 0, your velocity will be constant. And these reference frames, we call those inertial reference frame. Now, what is a reference frame? Reference frame is basically a coordinate system. For our purposes, you can just think of it as a coordinate system. You basically have a specific coordinate where you can measure the positions and time. Time is universal for everyone, so you don't need to think about time right now. But then let's say someone's standing here, he has a reference frame, and then say someone is moving in a bus. He has a different set of coordinates. His coordinates are like this. That is moving with respect to the non-primed coordinate. So reference frames for our purposes is just a coordinate system. Okay, and why do we need this law? Because this law actually sets the ground for other Newton's laws. So other Newton's laws, second law and third law. So second and third law are only valid in inertial reference frames. So basically, other two laws, they might or might not be valid in inertial reference frame. What Newton said was If you use an inertial reference frame, then second law and third law will be valid. Now, this makes your first law very, very important. Because if you don't know first law, then you don't know where you can apply second law and third law. But then wait, is this ever false? Because if this is always true, then we can just say, okay, we don't need first law. But then there are actually reference frames where this is not true. Example, so for a non-inertial reference frame, frames that are not inertial are basically called non-inertial reference frame. Okay, so what is a non-inertial reference frame? Or like what will be an example of a non-inertial reference frame? We can just take an accelerating bus. So we have a bus that is accelerating forward with acceleration A. And there is a person standing inside the car. So মনে করো তুমি গাড়ির মধ্যে দাঁড়ায় আছো. If the car starts to accelerate forward, you start to move back, right? You feel a force pulling you backwards. Now, in reference frame of the car, the person says, okay, I'm not moving. Because J's are reference frame, so he's stationary in his with respect to him. So the car is just saying, okay, I am being pushed to the backside. কেন? He can't explain. Is there any force acting on him? The guy inside the car, there is actually no force acting on him. He doesn't experience any force. However, still, সে যখন গাড়ির মধ্যে দাঁড়ায় আছে, with respect to the car, he feels an acceleration in the backwards direction. So he says, okay, my net force is 0, but my acceleration is not 0. I'm still moving to the back. So this is an example of a non-inertial reference frame. Okay, but then what does a person standing on the ground say? This reference frame is actually inertial. What would he say? He would say, okay, the car is just moving forward. You are not experiencing any force. The car is just moving forward. You're standing as you are. But then when you consider the reference frame of the man doesn't realize he's moving. So he just say, okay, I don't have any force on me, but I'm still being pushed to the back. So this is an example of a non-inertial reference frame. In fact, all accelerating reference frames are non-inertial. So anything that is accelerating, his reference frame is a non-inertial reference frame. So you cannot apply Newton's second law and third law there. Apparently, you can apply third law there, but Newton Jamne wrote the laws. He didn't specify if Newton's third law is valid in a non-inertial reference frame. But it turned out third law is valid in non-inertial reference frames. Second law is not. So now this is a huge problem because almost everything is accelerating. You're driving a car, the car is not moving at constant velocity. You have to start the car, you have to stop the car. So it will have acceleration at some point. So this basically means nothing is an inertial reference frame. Even the Earth itself, Earth is revolving around the sun. যখন সার্কুলার পথে ঘুরতেছে, এর স্পিড চেঞ্জ হোক না হোক, এর velocity কিন্তু চেঞ্জ হচ্ছে because it has to change directions. So the Earth itself is accelerating. So the Earth is not inertial reference frame. Then what did Newton do? Newton set the inertial reference frame as the reference frame of stars, basically. Reference frame of far away stars. So basically everything you measure with is respect to those stars. But then it's a huge problem. You don't want to do physics like this. And apparently you don't have to do physics like this. There are corrections to Newton's laws. You can consider unreal forces that don't actually exist. সেই ফোর্সগুলো দিয়ে তুমি কি করবা? You will make sure that this holds. Like if your f sum of f is 0, then your acceleration is also 0. এটা ইকুয়াল করার জন্য তুমি কি করবা? এক্সট্রা যে টার্মটা থাকতো সেটাকে একটা ইমাজিনারি ফোর্স হিসেবে চিন্তা করবা। Basically, what you end up doing is you will have something like this, that sum of f is 0 is equal to, you get something like, let's say, 10. And then you said it like this, that sum of f minus 10 is equal to 0. Okay, so you basically consider this as this is called a pseudo force actually. Basically a force that does not really exist. These are also called sometimes non-inertial forces. We will not get into those, but just know that it's not a limitation. It has been overcome, and then you will learn about it later. Like if you, I don't think you need it for junior science Olympiad, but you would probably need it if you want to learn deep physics, or if you want to participate in physics Olympiad or something. Okay, so that will be the end of our discussion for non-inertial reference frames. Just know that Newton's laws are not valid there. You can make them valid with some pseudo forces or non-inertial forces, but we will not go into those. Okay, so just to sum up, what does Newton's first law say? It says that there exists a reference frame where if sum of all the forces on a body is 0, then its acceleration is 0, or equivalently, if acceleration is 0, velocity is constant. And those reference frames are called inertial reference frame. Okay, and the next laws of Newton, so the second law and the third law of motion, are only valid in these inertial reference frames. Okay, then how do I know if a reference frame is inertial or not? Reference frames that are accelerating are non-inertial reference frame, and everything else is inertial. So every reference frame that is moving at a constant velocity with respect to another inertial reference frame is also an inertial reference frame. But the moment you add any acceleration, it becomes a non-inertial reference frame. Okay, so now let's get into Newton's second law, which is easier. So the actual second law, as I mentioned previously, is actually that sum of all forces is dp over dt. It's a derivative of momentum with respect to time. But we don't know momentum. So we don't know derivatives. So we just write this as delta p, change in momentum, divided by change in time. So basically we can write this as pf, final momentum, minus pi, initial momentum, divided by t, the time gap between these change. Now, where does F is equal to ma come from? Because Newton's second law bolle what we remember is actually F is equal to ma. But this looks nothing like F is equal to ma. The trick is to just write P is equal to mv. So you get mvf minus mvi divided by t. Just bring out the m, you have vf minus vi over t. Now vf minus vi over t, this is precisely by definition the acceleration. This is actually not the acceleration. This will be the average acceleration. But if you make the time gap very small, this will become the actual instantaneous acceleration. So basically we can write that sum of all the forces is equal to m times a. Now do remember, এখানে যখন আমি লিখতেছি sum of all forces, you basically vectorially add all the forces you have on the system. M is mass of the total system, and a is its acceleration. Okay, now there is a small problem here. Why don't we just always write this delta p over delta t? Why do we bother writing ma? because MA, from what it seems, is not even correct. Because if your mass changes, if these two masses are not equal, this and this, these two, then you can't you can take the mass out, and then you have a complicated equation that is not MA. But then Newton's second law, we always learn it's just F is equal to MA. So is this a special case, or does this always work? The answer to that will be a bit deep. That has to do with how we define a system or apply Newton's laws or Newton's second law. So when you apply Newton's second law, you first need to define a system. This is, let's say, my system. Let's say my system might have multiple blocks, might have one block, might have nothing at all even. Let's say we have this system that is a bit complicated, has a bunch of boxes connected. And then এর উপরে আমি net force বের করতে যাচ্ছি. First, this sum of F is just F external, which means no internal force. Now, what is an internal and an external force? Let me first get this here. Okay, so this is my system. So whenever I have a system of bodies, we will get to a specific example later in the class. But in general, if we have a system like this, we first draw a system line. What does it do? It specifies that this is the region where I'm applying Newton's second law. In our case, this is the region where we apply Newton's second law. Now, if two bodies inside this system are interacting, let's say এই উপরের ব্লকটা নিচে এই একটা ধাক্কা দিতেছে, নিচের ব্লকটা উপরে এটা ধাক্কা দিতেছে. These are called internal forces because এই force গুলার cause and application point যে বডির উপরে কাজ করতেছে সবকিছুই সিস্টেমের মধ্যে. So this force is an external force, sorry, internal force. But then let's say আমাদের নিচে হচ্ছে আর্থ আছে, so এদের সবাইকে গ্র্যাভিটি নিচে টান দিচ্ছে. There is an external force. Why? Because Earth is not included in my system. যেহেতু আর্থ আমার সিস্টেমের বাইরের একটা অবজেক্ট, এর এই সিস্টেমের অবজেক্টগুলোর উপর যে ফোর্স দিবে, that will be considered external force, not internal force. Now we don't need to add any internal forces here. Why? If we have two bodies connected like this, এই ব্লকটা এক একটু ধাক্কা দিচ্ছে, এই ব্লকটা এক একটু ধাক্কা দিচ্ছে. These two forces are supposed to be equal and opposite in magnitude due to Newton's third law. But then again, we haven't gone to third law yet, so we again pause the third law discussion for a moment and continue discussing this first. Okay, wait. Okay, so basically coming back here, this Newton's second law, we'll write it as sum of all the external forces of a system is equal to, the general statement is change of momentum divided by change in time. In most cases, you can write this as m times a. All right, so another question that we didn't address is this and this equivalent? Now, we did see here that these two are equivalent, but only in the case when mass is constant. So can we just say that Newton's law is F is equal to ma? First of all, you shouldn't say F is equal to ma. You should at least say sum of all the forces is equal to ma. Now, this in some context is correct, but this needs a bit more explanation. What explanation? You need to know যে আমরা এই সিস্টেমগুলো কেমনে ডিফাইন করি. Most of the time, these systems are defined by mass. It's very common to define systems by mass. What do I mean by mass? Let's say you have a disk, and then a disk, it breaks apart into three pieces. So initially your system was this whole disk. After it breaks up, this part flies off in this direction, this part in this, and this goes in this direction. So finally, যেটা এরকম ভাবে move করতেছে, which of the three parts is in your system? Let's say your box stays like this, and then this part is here after some time. Your bottom part is here, your top part is here. It should look something like this, and then this part is here. Does it mean this is part of a system and others are not? Not exactly. So the boundary, the system boundary we define is not a rigid thing. It's basically just a visualization যে আমরা দেখতেছি যে আচ্ছা this is my system line. এটা তুমি চেঞ্জ করতে পারো। Now when we define a system in physics, system বলতে আমরা normally বোঝাই by mass. So even if আমি বললাম যে আচ্ছা my phone is a system, এই ফোনের থেকে যদি একটা ইলেকট্রন বের হয়ে যায়, doesn't matter সেটা কোথায় আছে, that is still part of my system. If that electron goes to the other side of the universe, then still I have to include that in my system. That is only if I define my system by mass. But then by now you should already understand that if you define your system by mass, then your mass never changes. Because doesn't matter tomar particle koi gese, that will always have to be inside your system. Again, we're all talking about classical physics here. So no weird relativity stuff going on. So your mass will never change. Doesn't matter earth kon jagay chole jay, universe kon jagay chole jay, it's still part of your system because you defined your system by mass. And since we do it more often than not, we define our system by mass, you can say that if the sum of all the forces, all external forces is ma, m times a. All right, but then do we ever use a different case? Is there ever a case where we don't define system by mass? Yes, in fact, I think তোমরা অনেকেই হয়তো পড়বা eventually high school উঠলেই পড়বা যে you can apply Newton's law to a rocket. Let's say a rocket is flying off. A rocket is flying off in this direction. So rocketed in the mass change, right? So we don't want acceleration of these masses. We don't care about what the exhaust is. We only care about the rocket. So we take this as our system because we want the acceleration of the rocket. Our exhaust কি হইতেছে, we don't need any information about that. If we take the whole thing as a system, আমাদের এই acceleration ma এই টার্মের মধ্যে this term will include information about the exhaust as well. We don't need that, so we don't take that in our system. So we take just the rocket body as our system, but rocket body থেকে তো fuel eject করে দিতেছে. So this is an example of a system not defined by mass. And indeed, for this system, F is equal to ma will not be valid because there won't be any external force in free space. একটা rocket যদি travel করে, you don't have any external forces, but you still have acceleration. Your rocket is still accelerating. So on the rocket itself, basically you can consider it as তোমার exhaust সামনে একটা ধাক্কা দিচ্ছে. Because when you take this as your system, exhaust কিন্তু তোমার সিস্টেমের বাইরে এখন. So the exhaust when leaving pushes the rocket forward. So you can still pick some systems যেখানে you can make F is equal to ma valid. Okay, but that force, the exhaust কি ফোর্সে ধাক্কা দিতেছে, that is very hard to find. So usually we just go back to this del P over del T and use this. So again, when you define your system by mass, so when তোমার সিস্টেমের total mass change হইতেছে না, you can just write F is equal to ma. And that is often the case. In fact, that is not often the case. You can always find a reference frame or a system যাতে তোমার mass change হবে না. So you can always find a system so that F is equal to ma is valid. Again, we are talking about inertial frames and no only classical physics, no relativity and modern stuff going on. So if you are in an inertial reference frame, you can always find a system so that del P over del T is equivalent to ma because your mass isn't changing. All right, so that was discussion of second law. Let's go to third law. Again, we haven't seen the problems on this. It might seem that some কিছু miss করে যাচ্ছি, but this was just the preliminary discussion. We will solve problems with all things combined together in the end of the class, inshallah. So let's discuss Newton's third law first. Third law is very often misunderstood, more misunderstood than other laws of Newton. So the basic statement we talked about is every action has an equal and opposite reaction. So in more technical terms, you should say that every force has an equal and opposite force. So mathematically, you should write it like this. Now, what do this 1, 2, and 2, 1 mean? Now, we won't go into an example since I think we are getting late. So we'll just directly get into the actual statement. So what this tells you that, so for starters, যে কোনো force always দুইটা অবজেক্টের মধ্যে কাজ করে। So you will have two objects যাদের মধ্যে force কাজ করবে। For example, gravity, এই অবজেক্টটার উপর একটা force apply করবে। So we number these objects. We name number 1 as object 1, another as object 2. So let's say object 1, object 2 এর উপর একটা force দিচ্ছে। We mark it as F12. What is F12? F12 is basically force on object 1 due to object 2. And then similarly, object 2 is also applying a force on object 1. What do we name it? We name it F21. So what is F21? F21 is force on object 2 due to object 1. So the first number represents কার উপরে force, the second number represent কে forceটা দিচ্ছে. Now this third law should make sense. So the third law tells you that the force due to force on 1 due to 2, so the force on object 1 due to object 2 is equal and opposite to the force on object 2 due to object 1. Why do I say equal and opposite? Remember, যখন দুইটা ভেক্টরকে আমরা সমান চিহ্ন এবং একটা সামনে মাইনাস সাইন দিয়ে লিখি, it basically means their value same but direction ulta. So if you have this vector A, minus vector will have the same length but in the opposite direction. This will be minus A. So if one is F12, the other one will be minus F12, which in this case is F21. So these two forces are equal and opposite in direction. Equal in magnitude and opposite in direction. That is what the minus sign means. Now, the key point to notice here that people often forget is that these two numbers are different. So, কার উপরে force কাজ করতেছে, that is different. So, the first force is acting on object 2. The second force is acting on object 1. Now, there is no way these cancel out for a single body. If you take this system, your internal forces cancel out. That is what we did in Newton's second law. If you take this to be your system, তাহলে তোমার সিস্টেমের মধ্যে সব ফোর্সের যোগফল লাগবে. So you would add this and this, but these two clearly cancel out because they are equal and opposite. The total force will be F12 plus F21, which if you substitute this is just 0. And this you will see in like work energy or like conservation laws. This eventually actually leads to momentum conservation. So the third law is actually the basis of momentum conservation. All right, but momentum conservation is not what we discussed today. Let's focus on one of them. Let's say we take this as our system. This is our system. Then a objected upor kon force ase? It just has one force. So it can move because the only force acting on this is F21. The other force is acting on another body. Right? So there are very common questions that ask you about this misconception in some way. So a very common question is, there is a ghora. I'm not very good at drawing ghora. Let's just assume that this is a ghora. And then it is carrying a car. It's a gari tantese basically. So, all right. And then this is going this direction. So the question usually goes this way, that ঘোড়া আমার গাড়িটাকে টানতেছে, let's say F force. So the horse is pulling the car with a force F. But then by Newton's third law, the car is also pulling the horse at force F. Now, how can the horse move the car then? Because ঘোড়া যে ফোর্সে টানছে, ঘোড়াকেও আবার পিছন থেকে একই ফোর্সে টানছে. So can the horse move the car? Well, obviously from real life reasonings, we see that a horse can move a car. But then this suggests that it cannot. So there has to be something wrong here. What's wrong here is how you define your system. So if we take the horse as our system, the only force acting on the horse is this. So it has no problem in moving. Actually, there will have to be another force. Will have to be a friction force due to ground, যাতে ঘোড়াটা সামনে মুভ করতে পারে. If this was the only force, ঘোড়া just পিছে মুভ করবে. Okay, we will see another similar example, but in this case, ঘোড়ার পায়ে একটা friction কাজ করবে that will push it forward, and the car will pull it behind. Now, there is as long as F is larger than F, the horse can move. Because horse move করবে কিনা, করবে না, that depends on horseর উপর force. Similarly, if you consider the car, কারের উপরেও ground থেকে কিছু একটা frictional force থাকবে behind. Let's call it F prime. So as long as F is larger than F prime, car moves. So there is actually no contradiction. Okay, so where did the contradiction come from? The contradiction comes if you take this as your system. If this is your system, then you get that sum of F is equal to, in this case, you will get it to be F plus F minus F minus F prime. If you think about it carefully, because there are friction forces, right? So this and this cancels out as expected. The internal forces cancel out, but these two friction forces don't. So you basically have F minus F prime, and that will be equal to M times A. That will be equal to the total mass times A, the total acceleration of the whole body. Now, I should perhaps write it like this. This total force will be equal to mass of horse times the horse's acceleration plus mass of car times car's acceleration. But fortunately, since these two are tied with a rope, দড়ি দিয়ে বাঁধা আছে, আর ঘোড়ার acceleration যা হবে, কারের acceleration same হবে. So if you set this to be A, you can just write this as mh plus mc times A, which is basically m total times A. All right, now let's look at another similar example. without friction. What happens if there are no friction? So there is this frictionless floor. So this is frictionless floor. By the way, if you don't know about frictions yet, don't worry, we will get to friction again. So if something feels off, if there's something you don't understand, just watch till the end and then come back and see if you now understand it. So this is a frictionless thing. And then there's another person standing here. And এরা basically দড়ি ধরে টানাটানি করতেছে. So this person is pulling on the rope with force F. This person is pulling on the rope with force F as well. Now there is a slight, okay, there is something more deep going on here, but for our purposes, just assume that these two forces happen to be the same in magnitude. They will be same in magnitude if your rope has negligible mass. This is not because these are third law pairs. If okay, you know what, let's not confuse you guys. Let's just use different values here. Let's use F1 for this and F2 for this. Now if you think about the person, এই পার্সনটা কি করতেছে, পার্সনটা দড়িকে F1 বলে টানতেছে। এর থার্ড ল পেয়ার কই? How do you find it out? So where is the force working here? Between the man and the rope. So প্রথম ফোর্স দড়ির উপর কাজ করতেছে F এদিকে, এর রিঅ্যাকশন ফোর্স হবে অপোজিট বডির উপর, because remember F12 is equal to minus F21. So অ্যাকশন যার উপর কাজ করবে, রিঅ্যাকশন তার অপোজিট বডির উপর কাজ করবে. So if this is action, রিঅ্যাকশন কাজ করবে অপোজিট দিকে অন্য বডির উপর. So মানুষের উপর ফোর্স থাকবে জাস্ট এই দিকে F2. Okay, what about the first person? Again, you draw the system. তোমার মানুষ আছে, দড়ি আছে, দড়িটার উপর মানুষ F বল প্রয়োগ করতেছে এদিকে F1. সো এর রিঅ্যাকশন ফোর্স কি হবে? রোপটা মানুষের উপর এদিকে F1 ফোর্স প্রয়োগ করবে, ইকুয়াল এন্ড অপোজিট অন দ্য আদার বডি, নট অন দ্য সেম বডি. সো এই মানুষের উপর ফোর্স ডায়াগ্রামে ফোর্স আসছে এই পাশে F1. হোয়াট অ্যাবাউট দ্য রোপ? রোপটা যদি দেখো, রোপের উপরে সেকেন্ড মানুষ এদিকে F2 ফোর্সে টানছে, এদিকে F1 ফোর্সে টানছে. অলরাইট, নাও হোয়াট ডু উই ডু? উই ফার্স্ট সেট আ কোঅর্ডিনেট. লেটস সে আমাদের কোঅর্ডিনেট হচ্ছে এইদিকে পজিটিভ, এন্ড দেন আমার মানুষের অ্যাক্সেলারেশন হচ্ছে A1, সেকেন্ড মানুষের অ্যাক্সেলারেশন হচ্ছে A2, রোপের অ্যাক্সেলারেশন হচ্ছে AR, and their masses are M1, M2 and MR respectively. এপাশে যদি আমরা পজিটিভ ধরি, this basically means we will consider all forces pointing in this direction to be positive and the forces pointing in the other direction to be negative. Just regular vector notation আর কি. So 1D vector notation আর কি. So then for the first object, first person, you get F1 is equal to M1 A1. And individually প্রত্যেকটা অবজেক্টের উপর অ্যাপ্লাই করতেছি. Second person, you get minus F2 because it's pointing in the other direction. Remember, we took this direction to be positive. So F2 is minus F2. That is equal to A2, M2, A2. As for the rope, you get F2 minus F1 is equal to MR, AR. Okay, so this is system by system, but that is not where the confusion comes in. এটা কেন দেখাইলাম? Just to help you guys visualize this reaction force. This will be important in section 4 where we will apply Newton's law to different problems. Okay, now what if we try to take this as our system? এটা যদি আমরা সিস্টেম নিই তাহলে এখানে এক্সটার্নাল ফোর্স কত? There are no external forces. These rope and pushing forces, this is 0. These are all internal forces. So there's no external forces. So তুমি যদি টোটালটাকে তোমার সিস্টেম নাও, you get that sum of all the external forces is 0, and that will be equal to m1a1, mass of first body times acceleration of first body, plus mrar, acceleration of the rope times mass of the rope, plus m2a2, mass of the second body times acceleration of the second body. All right, then what if we substitute these values and see if it makes sense? If we substitute these values here, let's see what do you get. For the first one, we just get F1. For 8 MRAR, you get plus F2 minus F1. And for M2A2, you just get minus F2. So this cancels this out, this cancels this out. This is indeed 0. So this is consistent with our previous system as well. So it doesn't matter তুমি কোনটা system now, you get consistent results. That is nice. We want that. All right. An interesting thing happens if you set mass of the rope to be 0. So if we set MR to be 0, so this is a special case. If we set MR to be 0, what we get is that M1A1 plus M2A2 is equal to 0. That's from this equation. We get another interesting thing. From this equation, you get that F2 is equal to F1. Because MR is 0, so this right-hand side goes to 0. So this also has to go to 0. So that was what I was talking about in the beginning. Say, if the rope is massless, then both sides of force actually equal hoite hobe. That is due to this. All right, then this one actually has an interesting name. Let's multiply both sides with time. Then you get m1 a1 delta t plus m2 a2 delta t is equal to 0. But a1 delta t is actually change in velocity, and a2 delta t is actually change in velocity as well. This is first objective velocity change, this is second objective velocity change. How do I know? Remember, we had u plus at is equal to v, so you get at is equal to v minus u, which is basically delta v. So this equation is equivalent to m1 delta v1 plus m2 delta v2 is equal to 0. এটাকে যদি আমরা একটু গুছায় লিখি, we can write this like this: m1 v1i initial plus m2 v2i initial is equal to m1 v1f final plus m2 v2f final. And this is, if you recognize, your momentum conservation equation. So in the process, you also showed that momentum conservation is an immediate consequence of Newton's third law. In other cases, this derivation, like deriving momentum conservation from Newton's third law, might be a bit more tricky, but you can always do it in classical mechanics, at least. But in general, Newton's third law is more fundamental. There are scenarios when Newton's third law is not valid, but you still have momentum conservation. Okay, so all right, so that concludes our first section, discussion of Newton's laws. In fact, we have prepared ourselves for 4 as well. In fact, we have seen a lot of applications already. So last part should be simpler. Now we will start discussing different forces in mechanics. This section should be shorter. So forces in mechanics. So we'll talk about different forces we have, some common forces. First, we call it normal force. What is this? This is the force a general surface can give you two forces. One is perpendicular to the surface, another is parallel to the surface. This perpendicular surface is called the normal force. So to sum up, this is basically force applied by a surface perpendicular to it. This is usually denoted by N. Some books also denoted by R. I prefer N because R is usually also used to denote the resultant force. So you don't want to confuse those two. So N is usually better. Okay, do you have a specific equation to find the value of N? No. So no equations. So how can you find N? Remember that this force comes from a surface. So you usually have this বাঁকানো একটা surface, or you just have a ground. You have something, a surface that is preventing some sort of motion. And then you have to use the condition that no motion perpendicular to the surface. Example, let's consider the most simplest case. We have a box of mass m, এটা গ্রাউন্ডের উপর রাখা আছে. We want to find the normal force. এর নিচের দিকে একটা ফোর্স দিতেছে mg. So it should have a acceleration of g downwards. But এই সারফেসটা কি করতেছে? It is preventing that motion, downwards motion. কিভাবে? By applying a force perpendicular to it, which has value n. Remember, we cannot have any acceleration in this direction, in this perpendicular to the plane. If we cannot have, if a is equal to 0 in this direction, that implies that sum of forces in this direction is also 0. What are the sum of forces? You get n minus mg is equal to 0, or you get n is equal to mg. Okay, a slightly more interesting case. You have an inclined plane. Actually, inclined plane, you need to take components, which I hope you have learned in vector. So let's say we have a mass m again. So now it has weight, mg, but the normal force is always perpendicular to the surface. So the normal force is pointing in this direction. Now, we cannot have any net force in this direction, in the perpendicular direction. Surface is at perpendicular direction, কোনো motion থাকবে না. So no acceleration here. So the net force on this direction should be 0. If this angle is theta, then the net force in this direction is plus n, because n is pointing in the positive direction. Then mg এর এদিক বরাবর component. Let me just clean this a bit. Here, whoops. You have to move this to that side. Okay, so if this angle is theta, then you can basically project it here. You can project this force vector here. The projection will be this part, which is basically mg cosine theta. So you'll get minus mg cosine theta. And that should be equal to 0 because no acceleration in the perpendicular direction. That gives you n is equal to mg cos theta. All right, we are actually looking at examples during already. So let's look at one last example. Let's say we have a lift. লিফটের মধ্যে একজন মানুষ দাঁড়ায় আছে. And the lift, along with the person, is accelerating up with acceleration a. And mass of the person is m. So একটা মানুষ লিফটের মধ্যে দাঁড়ায় আছে লিফট সহ মানুষটা উপরের দিকে এ অ্যাক্সেলারেশনে চলতেছে। মানুষের ভর m হইলে what is the normal force on this surface? On this lift surface, what is the normal force? So let's draw all the forces. Let's clean these. Upper দিকে acceleration A. All right. The forces are নিচের দিকে mg force কাজ করছে, and উপরের দিকে there's a normal force n. What is the result of this force? এই দুইটা ফোর্স বাদে আর কোনো ফোর্স নাই। এই দুইটা ফোর্স মিলে they are accelerating the person up with acceleration A. So let's take upwards to be positive. That will give you that the net force is n, which is positive n because it's pointing up, minus mg because it's pointing down. And that should be equal to m times a because now it's accelerating up. The floor itself is accelerating up. So the person is also accelerating at acceleration a. So then you get n is equal to m times g plus a. So to sum up, there is no fixed way to find normal force. You are basically given conditions and you need to find the value of the normal force given depending on those conditions. Okay, so normal force is always perpendicular to the surface. There is another fact I missed, that the value of the normal force is always greater than or equal to 0. It's never negative. Actually, not the value. The value will always be positive, obviously, because it's like it's the value. Magnitude is always positive. But then the value of the normal force is 0 or positive, as in it can only push, it cannot pull. তুমি যদি একটা সারফেসের উপর কিছু রেখে দাও, ইউজুয়ালি ইউ ডোন্ট এক্সপেক্ট যে তুমি উপরের দিকে টান দিলে সারফেসকে নিচের দিকে ধরে রাখবে। You can do that, but তার জন্য তুমি you need to like glue it, or like you need to have some sort of like suction for that to happen. So that is a different issue. By itself, normal force can never be negative. So you will always point out towards the surface, never in. So normal force, it's always perpendicular to the surface. It's always greater than or equal to 0. And there is no specific equation to find the value of it. You will have to use condition or constraints of the problem given to you to find the normal force. Usually the condition is there is no acceleration in a certain direction, or there's a given acceleration in a certain direction, one of these two. All right, so after we discuss normal force, we can go to friction force. By the way, I think I'm going a bit too fast. That is because I'm low on time. If it feels like I'm going too fast, just you can, since it's a recording, you'd always slow it down and always rewatch it if you feel it's too fast. All right, so friction. What is friction? Remember, we said a surface can apply two forces. One is perpendicular to the surface, another is parallel to the surface. The perpendicular is called normal force. The parallel one is called friction force. And usually it's denoted by small f. Now, friction is of two kinds. There is static friction, which is a bit complicated. There is kinetic friction, which is simpler. So we do kinetic friction first. The kinetic friction force is just mu k times n. What is n? N is the normal force we just talked about. What is mu k? This is a constant. This is called kinetic friction coefficient. This is a constant and it depends on the type of surface. Actually, দুইটা সারফেসের উপর ডিপেন্ড করে, because friction force acts between surface of two bodies. Normal force, friction force, both are contact forces. এরা কোথায় কাজ করে? যেখানে দুইটা সারফেসের কন্ট্যাক্ট হয় সেখানে কাজ করে. So you need to have contact between two surfaces. This friction coefficient, this depends on properties of both surface. যদি দুইটাই অনেক খসখসা হয়, they have like they're very basically if they're very frictionless, then তাদের friction coefficient বেশি হবে. All right, and what is the direction? About direction, always opposite to the relative motion. So the direction of friction is always opposite to the relative motion, and the magnitude is mu k times n. Mu k বের করার জন্য you don't have any formula. It's usually given to you, or you are given enough information to find the mu k essentially. And then normal force, we just discussed about normal force, how to find that. All right, and static is a bit more complicated because static friction force equation is kind of similar looking, but then the value goes like this. This mu s is again called static friction coefficient. Similar quantity just for static cases. But then why do we have this smaller than or equal to sign? We will get to that. But first see which one is applied when. Kinetic is when you have relative motion. When you have relative motion. And static is when no relative motion. Example, let's say we have a box on a surface, যার friction coefficient হচ্ছে mu k, mu s দুইটা দিয়ে দিছে. Let's say s is the static friction coefficient, k is the kinetic friction coefficient, and it's sliding on the ground. ঘষা খেয়ে খেয়ে আগায় যাচ্ছে. It's just traveling like this. So there is a relative motion between the surface and the box. So there is a relative motion between two planes. Then the friction force is kinetic friction. So you don't have any static friction. There is relative motion. If you have relative motion, it's a kinetic friction. What's the direction? Direction is opposite to the relative motion. Relative to this surface, this body is going to the right. So the friction force will point to the left. And the value will be mu k times n. N you find through the force balance in the vertical direction. In this simple case, if its mass is m, you will find that n is just mg, giving you that the friction force is just mu k mg. But that's beyond the point. The point I'm trying to make here is if you have relative motion, you use kinetic friction. Now, what about static friction? When do you exactly use static friction? Let's say you have the same box. Now you are trying to push it in this direction with force F. But the force is very small, যার কারণে তোমার box move করতেছে না. So you are still applying this force, but your box is not moving. Let's say the normal force is just mg. It's a simple case. We keep it simple. Normal force is not our concern here. So let's say the normal force is mg, and the static friction coefficient is mu s. Now you keep increasing F little by little, but then it's still not moving. So since it's not moving, there has to be another force in this direction. Because remember, it's not moving means it's at acceleration 0. And then acceleration 0 implies sum of all forces is 0. So other than your applied force, there should be another force in the horizontal direction. This is the static friction force. And then what would be the value of this? The value of this will just be equal to your applied force. Because remember, it's not moving. Your object is not moving. You're applying a force F, it's not moving. That means the friction force is equal and opposite to your applied force. যার কারণে এটা ক্যান্সেল করে দিতেছে, your object cannot move. But then let's say you keep increasing F. You keep increasing F. This equation basically tells you there is a boundary. There is a maximum value of static friction. This maximum value, if is max, not if it's max, is given by mu s times n. So this is the maximum value. So let's say mu s n for a reference. Let's say this is 100 newtons. Then I'm F force apply করতেছি. When I'm applying 10 newtons of force, the friction force is 10 newtons. I'm applying 20 newtons, the friction force is 20 newtons. I'm applying 50 newtons, the friction force is 50 newtons. I'm applying 100 newtons, the friction force is still 100 newtons. But then, as soon as I cross 100, let's say I make it 101 Newton. It's not 101 Newton. Why? Because this now has crossed the maximum possible value of the friction force. That was 100. So what happens? It starts moving. Then you leave the static regime and start moving into the kinetic regime now, because now there is relative motion. Okay, so all this can be easily summarized as the friction force is smaller than or equal to mu Sn. Basically, we found the highest possible value of the friction force, static friction force, which will be mu Sn. And then your friction force can be lower than that as well. It doesn't always have to be mu Sn. And then after you leave the static regime, after you start having relative motion, you just go into kinetic friction, which is mu k times n. There is nothing weird going on here. You just have a simple equity here. All right. So other than this friction and normal force, obviously you have gravity of Earth. So this, you just simply write mg, mass times gravity. That's simple. You can have different applied forces. We don't go into those details. The other two forces we will discuss is tension and spring force. Spring force is simple, so let's get it done with first. Spring force is if you have a spring and it's extended, right? So it's extended as in it's compressed or stretched. So তোমার কাছে একটা স্প্রিং আছে, তুমি স্প্রিংটাকে either compress করেছো or stretch করেছো. Let's say by amount delta x. The spring force is given by minus k times this displacement. What is k? K is called the spring constant. It's a constant for a specific spring. There are a few methods to determine this, but we don't go into those. Those are a bit those are basically out of the syllabus for us right now. So we don't go about how to find spring constant. You will either be given the spring constant directly, or you will be given enough information to figure it out. So this is a positive constant. Delta x is the compression or an extension. What is the role of the minus sign here? This minus sign tells you that the force is in the opposite direction. So তুমি যদি compress করো, তোমার force stretch করার চেষ্টা করবে. So তোমার delta x যদি এইদিকে হয়, so you extended it, your force will point in this direction. So you will try to go back. That is basically a spring force. We will not be dealing with spring forces today, I think. Maybe in like practice problems or like problem sheet, সেখানে হয়তো পাবা, সেখানে spring related problem পাওয়া উচিত. But I don't think we will have time to cover spring related problems today. Okay, then we have tension. Tension, you usually see this in ropes. এটাকে আমরা টান বল বলি, rope অথবা rod. এরকম টাইপ অবজেক্টে টেনশন ফোর্স দেখা যায়। It's usually denoted by T. Again, no equation to determine this. But just like normal force, you'll have conditions. What is the condition? There is a fixed condition actually. This condition is that length of rope slash rod is constant. So let's take an example. Let's say there is a box and there is this person. এই পার্সনটা বেসিক্যালি একটা দড়ির সাথে বক্সটা বাঁধছে, and now দড়িটা এফ বলে এদিকে টান দিচ্ছে। ওকে, নাও টান দিতে দিতে লেটস সে আমার মানুষটা হচ্ছে এ অ্যাক্সেলারেশনে এদিকে মুভ করতেছে। সো সে দৌড়াতে দৌড়াতে সামনে যাচ্ছে এ অ্যাক্সেলারেশনে while holding one end of the rope. Now tell me this, যে রোপের ফ্রন্ট এন্ড এ অ্যাক্সেলারেশনে যাচ্ছে। So let's say after 1 second this front end of the rope is here. So this goes here after 1 second. Now if the length of the rope is constant, the back end of it should also move the same distance if the length of the rope is to remain constant. That means that the this back end also has to move at acceleration A. But how can it move at acceleration A? Basically, what ends up happening is this part now has to pull the block along with it. Normally কি হইতো? Normally what should have happened is block এখানে বসে থাকতো, তোমার দড়ি stretch হয়ে যেত। If you are using a very spring-like দড়ি or a very elastic দড়ি, that is what will happen. তুমি এটা ধরে টান দিবা, দেখবা তোমার দড়ি stretch হয়ে যাচ্ছে, box আর move করতেছে না। If it's a very heavy box and your rope is very like stretchy. But then if we force that the length of the rope is constant, then it requires যে আমার ব্লকটাও a acceleration এ move করবে, and for that you need to have a force in this direction. That is what we call the tension force. Where does it come from? It comes from the fact that the rope has to maintain its length. And what will be the value of this force in this case? If mass of the rope is m, we can just balance force on the block. We get T is equal to m times a, because remember, the acceleration of the man and the box has to be the same. So the force on the box, the total force on the box has to be m times a, which is just T. So similarly, just like in normal forces, you don't have a fixed equation for T. You just do force balance on different bodies to find the equation for T. Okay, so we have a lot of different forces other than this. You can have Coulomb force, you can have drag forces, and a whole other kinds of forces. We don't go into the details because these are the fundamental forces that you need to know to solve basic mechanics problems. I have actually covered these in very detailed. I don't think like a lot of the details you will probably not need for Junior Science Olympiad, but I still covered it so that, it helps you build a good intuition. All right, so the last part we are left with is force diagram. All right, so for force diagrams, we have been drawing force diagrams all along. This is a force diagram. It'll be a messy one, but this is a force diagram. Then this is a force diagram. This is also a force diagram. This is a force diagram. So mechanics is like a lot of mechanics problems comes down to just drawing force diagrams. This is a force diagram. This is also a force diagram. This is a force diagram. It's basically a diagram where you draw all the forces. This is also a force diagram. So it's a diagram. You have you have you have marked out all the acting forces on a body. So for example, if we do this, let's say there is a man, he's holding a rope that is connected to one block, that is connected to another block, and then these masses are m, m, and then there is a friction coefficient here, mu. This is just to notify that the surface is not frictionless. So this is the problem statement. How do I draw the force diagram of the whole thing? I'll just draw it here. Usually you'll have it in the questions. You have to first copy the question on the answer sheet, or you can also draw it in the question paper if you prefer it as a rough copy. But in general, your answer scripts should have force diagrams, because force diagrams give the script checkers an idea of how you are thinking about the problem. Okay, so the first forces you should think about is gravity. There is mass of all these objects, so you first draw the mass. There will be, okay, so the mass of the man be m, so there is also a mass here, mg. All right, so gravity done. There is clearly tension force here. দড়ি এই ব্লকটাকে ডানে টান দিচ্ছে, let's call it t, but then same দড়ি প্রথম ব্লকটাকে আবার উল্টা দিকে টান দিবে. Why? You can try to think about it. You can think, okay, I will just leave it for you guys to think. Just think about why these two, okay, why these two have to be equal. We have done that already. Remember, we showed here the actor rope, if it's massless, we showed it here. A rope, if it's massless, the force on both ends have to be equal. But then for the direction, I will leave it up to you guys to figure out why it is in the opposite direction. It's not that hard. I believe you can do it. All right. And then there's another tension force. This one here, this will be a different tension force. I denote this by T prime because it's a different rope, right? So it's T prime, and this will also be pulling on the person with T prime tension force. So I've drawn gravity, I have drawn tension force. I haven't drawn normal force. So normal force, let me use a different color. Okay, what is this color? Okay, I use this. So there will be this normal force N1, there will be one here, N2, there will be another one here, N3. All right, and then lastly, we also have friction forces here. Which color should I use here? This one. Okay, so the last force will be friction. Remember, the person is pulling on all the boxes, so the person is moving in this direction. Mass would say M. So everything is moving to the left, and everything is moving already. So the forces, first of all, will be kinetic friction, and they will be in this direction, opposite to the relative motion. So there will be first friction force here. এর value হবে হচ্ছে mu n1, because remember, for kinetic friction you don't need to worry about the greater than or equal, less than or equal to sign. It's just mu times n1, the normal force. And then for this one as well, you will have mu n2, and for the person you'll have mu n3. So this is your force diagram. This looks a bit messy. You don't want it to be messy. So let me show you. আমি এক্সামে থাকলে what we would have done. And এটার পরে দেখবো force diagram আঁকা হয়ে গেলে solving the problem is very, very simple. So first you need a very clear force diagram. Draw objects like they don't have to be in their appropriate sides. লাগলে বড় করে আঁকাও, as long as you can see everything clearly. So this is N2, N1, N3. I usually prefer to use different colors for different forces. This will be mg. Okay, this is large m. It's mg, This is mg. This is choto hatar mg. Then you have the tension forces. Okay, I changed the colors, unfortunately, but then you get the idea. This one will be T prime. This one will be T prime. This will be T, and this will be T. And then the last force is the friction force, which will be ADK mu N1, ADK mu N2, ADK mu N3. So this is the force diagram of the whole thing. Usually there is another thing called equation of constraint. I wouldn't go into much detail with this because usually for simpler problems, equation of constraint is like not something you should be very bothered about because usually it's very easy to find. Basically, constraint means a shorto, a condition. In this case, the question is supposed to have another condition that the ropes are inextensible. Now, inextensible rope means acceleration of both ends is the same. Actually, both ends are the same. Oh, actually, we missed another force because remember the person is walking forward, right? So there has to be some force pushing the person to the front. So let's say there is this applied force that is pushing the person to the front with force F. The person is not simply walking. He is being pushed to the front with force F. Should also draw it here. He's being forced in this direction with force F. Okay, so another information, I haven't stated any problems yet. I'm just discussing this whole thing. We have the force diagram. We are basically gathering everything before we go to the actual problem. So acceleration of both ends is the same. That means if acceleration of the person is A, acceleration of the block will also be A, and acceleration of the third block will also be A. So যেহেতু সবগুলো দড়ি দিয়ে connected, the conclusion you get is everyone moves at acceleration A. All right. So if that's the case, now we can start applying Newton's laws. So we are done with the free body diagram. Once you are done with the free body diagram, we just go about applying Newton's second law. Okay, what is the question? Let's say that the question is, what are we given? We are given that M is equal to, let's say, 1 kg. Choto hater M is given by, let's say, 50 kg. The applied force, let's say, is 1,000 newtons. And we want to know, okay, another thing, we know that mu is, let's say, 0.5. All right, and then we want to know what is A. We want to know what is T. We also want to know what is total friction force. All right, so yep, I'm recording. All right, so okay, let's start solving this problem. There are multiple approaches of doing it, and all of that revolves around what you choose to be your system. For this problem, for the first problem, to find acceleration, the simplest system you can choose is including everything. If you include everything, the only external force here is this. Okay, not that actually. Oh, okay. Actually, you know what? Let's forget it because we will have to consider each body because there is another external force. There is this friction force that is between the floor and the boxes. That is external to that system. So we focus on each object first. So let's try this. This is our system 1. I will not redraw it, but in exam, usually I would just pick this up and redraw it. Here I'll just use this box. So এই বক্সের মধ্যে থাকে এক্সটার্নাল ফোর্স কি? এক্সটার্নাল ফোর্স হচ্ছে T, mg, n1 and mu n1. First, remember vertical direction acceleration 0 because the floor is blocking any vertical movement. So that immediately gives you that n1 is equal to mg. Why do we get it from? Vertical force balance. Now consider horizontal force balance. Horizontal, you have total force is T minus mu n1. This is assuming this direction is positive. Can we take a positive this because it's accelerating in this direction, so it's easier. You can also take the opposite direction, you'll get the same answer anyway. So this total force will be equal to m times a. So this is my second equation. I'll just keep boxing the equations I get. All right, so for the second equation, second system, we take this. Similarly, I'll just write the total force balance equation. You'll get N2 is also equal to mg from vertical force balance. From horizontal force balance, you'll get T prime minus T minus mu N2 is equal to ma. Why the same acceleration? Because remember, everyone has the same acceleration because they are connected with a rope. Finally, go back to the first object. If you take man to be the system, you get N3 is equal to mg. And you also get that f minus T prime minus mu N3 is equal to ma. সো প্রত্যেকটা অবজেক্টের উপর আমরা নিউটনের ল লিখেছি কয় ডাইরেকশনে লিখেছি? দুই ডাইরেকশনে, একবার এক্স ডাইরেকশনে আর একবার ওয়াই ডাইরেকশনে, and then we get these set of equations. How do we find a? Now তোমাকে just equation solve করতে হবে. It's not that hard actually. The easiest way to do is actually add these three equations. What happens if you add these three equations? On the left, you will have T minus mu n1 plus T prime minus T minus mu n2 plus f minus T prime minus mu n3. And on the right, you'll have m plus 2m into a. Now on the left, see this cancels this cancels this. So you just have f minus একটা mu common দিতে পারো. You have n1 plus n2 plus n3 is equal to m plus 2m into a. But remember, we already know the n's, n1, n2, n3. So you just plug these in here. That should give you f minus mu g into m plus 2m is equal to m plus 2m into a. Just solve for a. You'll get a is f divided by m plus 2m minus mu g. This is your acceleration. Once you have the acceleration, the rest of the parts are not that difficult either. You know a. If you plug a back in here, it's just equation solving. There's nothing fancy going on. So if you just plug a back in the first equation, second equation, that gives you T minus mu. What is n1? Remember, n1 is just mg. So minus mu mg is equal to m times a. So you have m times f divided by m divided by 2m minus mu mg. What are we supposed to find? We're supposed to find T. That will give you that T is equal to m times f divided by m plus 2m minus 2 mu mg. Okay, so you just plug in the values. I'm not plugging in any values because I don't have a calculator with me right now. You just plug those values in here. In here, you'll get m and t. So that solves this and this. The last part is what is the total friction force? It actually আমাদের already হয়ে গেছে. This is actually the total friction force. How do I know? তিনটা friction force আছে দেখো. mu n3, mu n2, mu n1. তিনটা same direction এ কাজ করতেছে. So the total friction force is mu n1 plus mu n2 plus mu n3, which gives you mu times n1 plus n2 plus n3. And remember, we know n1, n2, n3 already from this equation. This, and this. Just plug those values in, and we'll have the total friction force. All right, so that is our application of Newton's laws, basically. I would have liked to show you another example, but then I think we are out of time. So I will finish here today. You will get a problem sheet. You should have more practice problems there, and you should definitely try those problems. And if you face problems, you can always ask the mentors to help you. And even better, you can collaborate between yourselves, because even in my time in Olympiad, one of the biggest learning contributing factors was learning from peers. So like discuss with your friends, try and see what they think, discuss what you think, and then try to go to a mutual conclusion. If you can't solve it, then I would suggest just reach out to a mentor and ask them how you can solve these questions and so on. Okay, so I will end the class here. Okay, thank you.